Well, hello, ladies and gentlemen. Let's move on from the material from last time. We finished up with a expression for calculating the maximum efficiency, maximum coefficient of performance for any device operating between a hot and a cold reservoir. Let's actually spend the time today developing in detail a machine or a cycle, a work-producing cycle, or a refrigeration or heat pump device, a cyclic device. Let's work today on developing a reversible device operating in a cycle, and we'll analyze it in detail. So that's the plan today. Let's take some of the concepts we've learned about reversible versus irreversible processes, and let's apply this to developing a cycle that operates reversibly and therefore produces the maximum power or has the maximum coefficient of performance. Okay? So let's look at the following. Let's say we have at state one, we have a piston cylinder device, and it's got some kind of a working fluid. I don't know, maybe it's air in here, who knows? But we start off at state one. Now at state one, we have a temperature T1 and a volume V1. And this piston cylinder device is in contact with a hot or a high temperature reservoir, TH. Okay, so at state one, the system is in thermal contact with a hot reservoir TH. What that means is, by the way, is that temperature T1 is equal to TH. Okay, so we start off with an initial temperature T1, which is equal to a temperature of a high temperature reservoir in thermal contact with our system. Now, we're going to go to state two. What is state two? Well, we're going to let our system, our air, expand isothermally from state one to state two. So this is going to be an isothermal process. Going to have some expansion going on here. So T2 is equal to T1 equal to T high. Okay, so here's our high temperature reservoir in contact with our system, the air, and the piston cylinder device. So this is a isothermal expansion. Isothermal expansion. Okay. Now, of course, as the fluid expands, the air expands. It's isothermal, but as it expands, it's doing boundary work, and therefore we're going to be transferring heat into the system. So there is some heat being transferred, Q1 to 2, and of course there's some boundary work being done, so there's also a work 1 to 2. Okay, so there's heat and work interactions going on from state 1 to state 2. Now let's take away the reservoir completely. Let's take away the reservoir and expand our piston cylinder, our air or our material in our piston cylinder device. Let's expand it even further. Take away the reservoir, and let's wrap insulation around this thing. Okay, so let's expand adiabatically, no heat transfer. Let's expand adiabatically the air from state 2 to state 3. So this is adiabatic expansion. What that means is no heat transfer. Q2 to 3 equals 0. Why? Because it's adiabatic. And of course, the system is doing some work. It's expanding, so there is some boundary work going on from state 2 to state 3. Okay? Now we're going to expand it until we get to a low temperature. So T3 is equal to some low temperature TL. We're going to expand it until it cools down to some low temperature TL. Okay? Now, once we get down to the low temperature, TL, I'm going to start compressing it. So I'm going to start compressing it. I'm going to squeeze down the material. So this is state 4. I'm going to squeeze down the material. I'm going to put it in contact with a reservoir at a low temperature, TL. So remember, T3 is equal to TL. And I'm going to put it in contact now with a low temperature reservoir. Okay? And from 3 to 4, I'm going to squeeze it down. I'm going to squeeze it down from 3 to 4. So there'll be some sort of a heat interaction from 3 to 4 and some sort of boundary work from 3 to 4. And the process 3 to 4 is going to be isothermal compression. Isothermal compression. Isothermal compression from 3 to 4. Isothermal compression. So our temperature, T3 is equal to T4 is equal to the low temperature reservoir temperature. And then finally, I'm going to squeeze it down some more. I'm going to put some insulation around this thing. I'm going to squeeze it down until I get back to the high temperature. So I'm going to compress the system until I get back to the original state, state 1. So this is going to be adiabatic compression. So I'm going to put some insulation around it. That means no heat transfer. Q4 back to 1. No heat transfer because it's an adiabatic compression process. And I'm going to squeeze it, raise the temperature, and get back to the original temperature and the original volume. I guess I should put the volumes in here too. So we have a volume V3. And of course, we have a volume V2 as well. I'm sorry, V4. That's state 4, not state 3. State 4, state 3, state 2. We got pressures too, but you can imagine, you can put that in if you want. Okay, let's make a TV diagram and a PV diagram for this cyclic process, state 1 to 2 to 3 to 4. Let's make the PV and the TV diagram for this process. Specific volume, let's say, or you can put volume here, doesn't matter. Volume or specific volume, the trend is the same. So let's see, state 1. Let's go back and look at how we're going to start drawing this. At state 1, we're at a high or a maximum temperature, a high temperature, and we're at apparently the smallest volume. So state 1 is at the smallest volume and the highest temperature. So I'm going to put my state 1 right here on the TV diagram, okay? Now process 1 to 2 is an isothermal expansion. Process 1 to 2 is an isothermal expansion where there's some heat transfer going on from the high temperature reservoir. So this gas is expanding and it's receiving heat from the high temperature reservoir. So we have the heat transfer Q1 to 2 and we're expanding it all the way out to state 2. Okay? So it's an isothermal expansion, therefore it's a horizontal line on the TV diagram. Let's look at process 2 to 3. Process 2 to 3 is adiabatic expansion. So volume increases and temperature falls because we don't have any heat transfer. The boundary work is resulting in a reduction in internal energy. So we have an expansion with a fall in temperature. So this is state 3. By the way, these temperatures here, so this is T high. And down here, we expand it until we get to the low temperature, reservoir temperature. Okay? 2 to 3, we expand it until we get to the low temperature, reservoir temperature. No heat transfer. No heat transfer going on 2 to 3. It is adiabatic. Process 3 to 4. That's isothermal compression. So we place the air, or the material in the piston cylinder device, in contact with the low temperature reservoir, and we're compressing it isothermally. That means we're doing work on the fluid, so it's got to be rejecting heat out to maintain the same temperature. So we have a Q 3 to 4, it's isothermal compression. And then 4 to 1, back to the original state, is adiabatic compression. So volume goes down, temperature goes up, because we're doing work on the fluid, the gas, whatever it is. We're doing it without heat transfer, so temperature's got to go up as we do work on the working fluid. Okay? So this is state 4. All right? So let's make sure we indicate where the heat transfer is not occurring. 2 to 3 is adiabatic, and 4 to 1 is also adiabatic. So I'm going to put some little cross hatches there. All right? What about the pressure volume diagram? Let's look at that. Pressure volume. Well, the minimum volume occurs at state 1, and the maximum temperature is at state 1. Pressure is equal to mass. Pressure is proportional to temperature and inversely proportional to volume. PV is equal to MRT. So state 1's got to have the maximum pressure. So there's state 1 right there. Maximum pressure is at state 1. And you can confirm that. Minimum volume, maximum temperature at state 1. You can just inspect the ideal gas law, for example. You'll see that state 1 has to have the maximum pressure. Now, volume is going up isothermally from state 1 to state 2. That means pressure has to fall. So pressure has to fall from state 1 to state 2. And this is where the heat transfer is occurring here. State 2 to state 3 is no heat transfer, increase in volume, so pressure falls very quickly. Temperature will fall and volume goes up, so pressure has to fall very quickly from 2 to 3, okay? Then we have isothermal compression. Isothermal compression from 3 to 4. Now that's where the heat gets transferred out to the low temperature reservoir. And then we put insulation around it, take away the reservoir, and we compress it further up to the maximum temperature. That results in a very rapid increase in pressure. Back to state 1. Okay? Now, one thing I do want to do before we move on, I want to point out these heat transfers here. Q1 to 2, Q2 to 3. Remember, these heat transfers occur when the system is interacting with a reservoir. In particular, the high temperature reservoir when it's receiving heat from 1 to 2, and it's rejecting heat to the low temperature reservoir from 3 to 4. So if you like, you can actually write QH here, and you can write QL. Just to indicate where the heat is coming from or where it's going, the high temperature or the low temperature reservoir. So you can, in the place of Q1 to 2 and 3 to 4, you can indicate Q high and Q low. Now, if this device contains no sources of friction, the piston moves up and down in the cylinder without friction. There's no friction here. And it operates very slowly. In other words, this piston is not getting jerked up or jerked down. There's no unrestrained expansion of the gas anywhere in the cycle. Then this cycle here is technically reversible because it contains no irreversibilities. You might ask yourself, well, what about heat transfer? Remember, the heat transfer occurs when the system temperature is equal to TH or TL. So there's no temperature difference between the gas or the working fluid and the reservoirs. So the heat transfer occurs at the reservoir temperatures, and there's no delta T between the working fluid and the reservoirs. There's no delta T, no finite temperature difference. So there's no irreversibility here due to friction, no irreversibility due to unrestrained expansions, and no irreversibility due to heat transfer across a finite temperature difference. Okay, let me rewrite this here. Let's just condense what we have. Let's condense what we have. I'm going to leave those PV and TV diagrams up. So let's write the processes out. Process 1 to 2, isothermal expansion. And I'm going to write in parentheses here, at T equals T high. T high is the high temperature reservoir temperature. Process 2 to 3, adiabatic expansion. Process 3 to 4, isothermal compression at temperature equals T low, the low temperature reservoir temperature. And then to return to the original state, to complete the cycle, we have adiabatic compression. Adiabatic compression back to the original state. So you can see these processes most clearly on the TV diagram, where you have an isothermal process, 2 isothermal processes, and 2 adiabatic processes to form the cycle. Now let me make it explicit here. Let's move over to the next board. Let me make it explicit here. If the device composed of a piston cylinder device here. So we have a piston cylinder device. That's what we've been dealing with here, piston cylinder device. And that piston cylinder device excludes what? Friction, unrestrained expansion, that means we're not jerking the piston up and down. If we jerk it up really high, if we jerk the piston up too fast, we'll form a partial vacuum up here, and that'll cause unrestrained expansion. Okay? So no unrestrained expansion, it includes unrestrained expansion. What I mean by that is slow operation. How slow? Extremely slow. So slow you can't see the piston moving. That slow. And it also excludes the final third form of irreversibility. So I guess I'll write here excludes irreversible processes. And what I mean by that is processes including friction, unrestrained expansion. That means we need slow operation. And then finally, it excludes heat transfer across a finite temperature difference. Q across a finite, measurable, detectable, finite delta T. In our case, the heat transfers always occur when the system temperature is equal to the reservoir temperature, so we don't have a delta. The delta T is 0 in that case. So delta T goes to 0 during the cycle. So what is this particular cycle called, this device? It is called a Carno heat engine. Carno heat engine. Carno heat engine. C-A-R-N-O. Sadi Carnot, very famous French thermodynamicist. He helped develop the concept of entropy, which you're going to be learning about very soon. Carnot heat engine excludes irreversible processes, friction, unrestrained expansion, heat transfer across a finite temperature difference. The big picture is we have this Carnot heat engine, and it's operating in a cycle. Carnot heat engine. It's operating in a cycle. It receives heat, Q high, from a high temperature reservoir. Produces a net amount of work. How do I know it produces work? Well, let's look at the PV diagram. Look at the area bound by the PV curve. It has an area, a positive area. The area is all this stuff here. This is boundary work. So this cycle is producing boundary work or work. It's a work-producing cycle. It's a work-producing cycle. So it's producing work over the cycle, and it is rejecting some excess heat to a low temperature reservoir, rejecting Q low to a low temperature reservoir. That's the big picture. So this Carnot heat engine operates between a high and a low temperature reservoir, extracting out a certain amount of heat from the high temperature reservoir, taking some of that energy, the heat, producing work over the cycle, and then rejecting the remaining energy to the low temperature reservoir, okay? Needless to say, this does not violate the Kelvin-Planck statement of the second law. We're operating between two reservoirs. The Carnot cycle excludes all sources of irreversibilities. The processes are isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Well illustrated on the TV diagram. I suggest you commit to memory the TV diagram for the Carnot cycle, and then you've got the work represented by the area bound by the curve on the PV diagram. So we can see that this cycle produces work. The area bound by the PV curve over the cycle is positive. So this thing produces work. all right? Now, needless to say, because this is a reversible device, the efficiency can be easily calculated. So note, the Carnot cycle, or Carnot heat engine, is reversible. It doesn't include any sources of irreversibility: friction, unrestrained expansion, heat transfer across a finite temperature difference. All the heat transfers occur at the reservoir temperatures, so there's no temperature jump during the heat transfer process between the source and the heat engine, okay? So let's calculate the efficiency of this thing. So the efficiency of the Carnot cycle, or Carnot heat engine. Carnot heat engine. Well, it's a reversible heat engine. It's a reversible device. So it's actually, the efficiency is equal to that of the reversible heat engine. It's reversible. Now, what's the expression for the efficiency of a reversible heat engine? We developed this last time. So the efficiency is work over the cycle divided by the heat addition. So work over QH, and that's for the reversible heat engine. The work is equal to QL. If we apply an energy balance to the Carnot heat engine, we find that the work over the cycle is equal to QH minus Q low. Okay, so that's the work. I think I'm going to move this right here. Work equals QH minus Q low. Over the cycle, because delta E is equal to 0, so heat is equal to work over the cycle. And the heat is equal, the net heat added over the cycle is Q high minus Q low. So work is Q high minus Q low divided by Q high for the reversible process, or if you like, 1 minus Q low over Q high for the reversible process. What's Q high over QL over Q high for a reversible process? It's equal to the temperature ratio of the reservoirs. 1 minus TL over TH. So the efficiency of this thing, eta Carnot, is equal to eta for the reversible heat engine, which is equal to 1 minus TL over TH. So what does this say here about the efficiency of the Carnot heat engine? Let's see what this says about the efficiency of the Carnot heat engine. So efficiency is 1 minus TL over TH. So eta Carnot is equal to 1 minus TL over TH. Same thing for a reversible heat engine. And again, the picture here is we have a high temperature reservoir, we have a Carnot heat engine producing a certain amount of work over the cycle from a certain amount of heat taken from the high temperature reservoir and rejecting the excess heat to the low temperature reservoir. So that's what's going on here. So note, when the reservoirs have the same temperature, they're essentially the same reservoir. When they have the same temperature, the efficiency is 0. It produces no work, no matter what the heat interaction. Why might that be true? Because that would be a violation of the Kelvin-Planck statement of the second law. If these guys have the same temperature, that means it's the same reservoir. So we got one reservoir interacting with the device that cannot produce work. Now, under what conditions does this thing produce the most work in terms of efficiency? When is it most efficient? Note, efficiency, Carno, goes up as the temperature ratio goes down. So the larger the temperature difference between the two reservoirs, the hotter the high temperature reservoir is and the colder the low temperature reservoir is, the bigger that temperature difference, the greater the efficiency is for this Carnot heat engine. So if you want the most efficient heat engine, Carnot heat engine, or any reversible heat engine, you want to maximize the delta T. So maximize eta by maximize TH minus TL. You want to maximize the temperature difference between the high and the low temperature reservoir. Okay, let's do an example here. Let's take a pause here and let's do an example. All right, so let's do an example here involving the Carnot cycle. We have a Carnot heat engine. Air is the working fluid. That's what's inside the piston cylinder device. So let's put up our schematic. So we have air in our piston cylinder device. So air, if we apply any kind of conservation relationships like the energy balance, the air inside the piston cylinder device is going to be our system. Okay? So you have a Carnot cycle, air is the working fluid or the system. The heat transfer to the low temperature reservoir during the cycle is 3.4 kilojoules. The high and low temperature reservoir temperatures are 300 and 250 degrees Kelvin. This is going to be a constant specific heat problem. I'm going to find a quantity called K. K, which is the ratio of the specific heat at constant pressure, Cp, divided by the specific heat at constant volume, Cv, and I'm going to set that equal to 1.4. I'm going to assume constant specific heats, and I'm going to fix the ratio of Cp to Cv. This will help with calculations. This will make it relatively easy to do calculations, as opposed to using air tables, which can be much harder to do, okay? The amount of air, the working fluid, is 0.1 kilograms. The minimum and maximum volume in the cycle is 0.01 cubic meters and 0.0254 cubic meters. So the min and max volume in the cycle. I think before we get started here doing any work, I'll tell you what we want to do for a second. Let's actually put the cycle up on the TV diagram. I think it's a really good idea to put up the TV diagram so that we understand what's going on from state to state. So temperature, volume. Remember, state 1 is the minimum volume, maximum temperature. 1 to 2 is isothermal heat addition from the high temperature reservoir. That's 1 to 2, isothermal heat addition at TH. And then we have adiabatic insulated, adiabatic expansion from 2 to 3. Then we have isothermal compression at temperature T low, and that results in heat being rejected to the low temperature reservoir, and that goes from 3 to 4. And then we have adiabatic compression back up to state 1, insulated. Okay, so I would definitely, if you do any problems with the Carnot cycle, you need to put up a TV diagram to keep track of what's going on. Now, what are we supposed to find in this problem? We're supposed to find the pressure at state 1. So I want to know the pressure at the top of the cycle here. That's presumably the maximum pressure at that point, maximum temperature, minimum volume. Presumably the pressure is maximized. Then I want to know what the heat transfer is from the high temperature reservoir. And I want to know what the efficiency is of the cycle. There's actually two ways to calculate the efficiency. Oh, I'm sorry here. Let's kill this. All right, let's do a problem here, ladies and gentlemen, involving a Carnot heat engine. So we got a Carnot heat engine with air is the working fluid. Air is what's inside the piston cylinder device. So if we do a little schematic here, we have our piston cylinder device. Here's our piston. And the working fluid inside of the Carnot heat engine, our piston cylinder device, is going to be air. Okay? So air is the working fluid. It could be H2O, could be water vapor, it could be using some kind of other material, nitrogen, carbon dioxide. We're going to be using air as our working fluid. The heat received from the low temperature reservoir is 3.4 kilojoules. So let's put up a little picture here. Here's our high temperature reservoir. Here's our low temperature reservoir. Here's our Carnot heat engine. Carnot heat engine. It is rejecting heat to the low temperature reservoir, QL, and that's equal to 3.4 kilojoules. So we know that. Of course, it receives energy from the high temperature reservoir to produce a certain amount of work. If you like, work over the cycle. Work over the cycle. I'm going to put a subscript cycle there. You probably should do that too. So it receives it rejects 3.4 kilojoules to the low temperature reservoir. The low and high temperature reservoir temperatures are 300 and 250 degrees K. So this is 300 degrees Kelvin, and this is 250 degrees Kelvin. So T low, 250 degrees Kelvin, okay? The ratio of specific heats is going to be constant. Cp over Cv is going to be held constant. In other words, we're doing a constant specific heat analysis. The ratio Cp over Cv always called K. The ratio of Cp over Cv is called K, and that's going to be given to you as 1.4. So we're going to do a constant specific heat problem. Many problems can be done using the ratio of specific heats without knowing what the actual value of the specific heats are. Okay, and you'll see this in just a little bit. Okay, mass for the air. The working fluid, 0.1 kilograms. The minimum and maximum volume in the cycle. Minimum and maximum volume in the cycle. 0.01 cubic meters, 0.0254 cubic meters. So let's put up the TV diagram. You should always put up a TV diagram when you do these kinds of cycle problems. TV diagram, some kind of diagram. So state 1 is the minimum volume, maximum temperature. 1 to 2, as you recall, for the Carnot cycle is isothermal heat addition from the high temperature reservoir. So the temperature here is T high. The air is at high temperature, T high. As we go from state 1 to state 2, isothermal heat addition from the high temperature reservoir. Then we have adiabatic expansion down to T low. Adiabatic expansion down to T low. And then we have isothermal heat rejection to state 4. So we compress it. We compress the working fluid. Temperature is held constant. Why? Because heat's being rejected from the air as it gets squeezed down. And then we go back up to state 1 to complete the cycle with a adiabatic compressive process. Adiabatic compression process. So that's a cycle there. That's a cycle. All right, let's get started here. Let's get started. Let's calculate pressure at state 1. I think that's the easiest thing to do, so let's get started with pressure at state 1. Pressure at state 1. Well, I guess I can assume IGB. I'm going to do it. So if we assume ideal gas, it's pretty easy to calculate the pressure. Well, we'll see if it's easy. Hopefully it's easy. So analysis. I'm going to assume IGB. In fact, I'm going to write it in the assumptions in just a moment. But let me write down the ideal gas law. PV is equal to MRT. I can evaluate this at state 1. I want to know pressure at P at state 1. So I can solve this. P1 is equal to MRT1 over V1. Now, what are these pressures, temperatures, and volumes? What are these pressures, temperatures, and volumes? Or temperatures and volumes, sorry about that. Let's go back to our TV diagram and see if we can figure out what T1 and V1 are. Let's see here, T1 is equal to TH. That's the high temperature. What about V1? So what is this? Well, that's the minimum volume in the cycle. We're given the minimum volume in the cycle. So this guy here is Vmin. By the way, that's 0.01 meters cubed. So I know Vmin, or if you like V1. V1 equals Vmin. So I know this volume, V1, and I know the temperature, T1. It's T high. So this is M RT high over Vmin. Well, I know the mass, 0.1 kilograms. The gas constant for air is what? 0.286 kilojoule per kilogram degree in Kelvin. T high is 300 degrees Kelvin, and the minimum volume is 0.01 cubic meters. I'm going to get kilopascals out of that equation. I'm going to get kilopascals out. And I get 858 kilopascals. 858 kilopascals. 858 kPa. P1 equals 858 kPa. Okay, let's put a box around that. So that's the pressure. It's actually the maximum pressure in the cycle. We saw that from the PV diagram. So P1 is the maximum pressure, 858 kilopascals. Okay? Let's calculate the high temperature reservoir heat transfer, QH. Let's calculate the high temperature reservoir heat transfer, QH. In other words, Q what? In other words, Q1 to 2. Let's find out the heat transfer from state 1 to state 2. Okay, here. Process 1 to 2. This is isothermal. Isothermal heat addition. Isothermal heat addition from the high temperature reservoir. Now, if I write down the energy balance, let's just write it down. Well, let's write down the energy balance. I think that's the best way to go. So let's see here. Q1 to 2 minus W1 to 2 is equal to delta E, which is equal to delta U. Actually, I need to start doing some assumptions here. I was going to assume IGB, and also from that equation, I'm going to assume negligible changes in kinetic and potential energy. Let's do that right now. Assumptions. IGB and delta KE equals delta PE. No changes in kinetic and potential energy for any of the calculations over any of the processes, okay? Now we're working with constant specific heat. So this is mCV delta T from 1 to 2, okay? Delta T from 1 to 2. Now, if it's isothermal, what's delta T from 1 to 2? It's 0. 0, isothermal. So delta U is equal to 0. No change in internal energy because it's an isothermal constant temperature process. So what we get here, and by the way, Q1 to 2 is Q high. What we get is the heat transfer from the high temperature reservoir is equal to the work, 1 to 2. Now this is a piston cylinder device. I don't see any wires. I don't see any shafts in there. Carnot cycle didn't have anything to do with wires or shafts. So this is only boundary work. So this is boundary work. W bound. So that's going to be equal to the integral of PdV from V1 to V2. Now, it may not look promising at the moment. This is an isothermal process. It's not an isobaric process. It's not an isochoric process. It's an isothermal process. So pressure is a function of volume for an isothermal process. Let's see, from the ideal gas law, pressure is equal to mRT over V. That's from the ideal gas law. So let's put this in the integral. mRT over V dV from 1 to 2. Now this is an isothermal process. Temperature is at T high the whole time during the process. It's a constant. That means along with mRT, I can pull those things out of the integral. So I get mRT high integral dV over V from V1 to V2. The antiderivative of 1 over volume is a natural log. And so I get mRT high natural log V2 over V1. So that's the expression for my heat transfer from the high temperature reservoir. Now let me write this over in the corner here. Let me go write this in the corner. It's going to be an important relationship. Let me just write it right in the corner out of the way. Q high equals mRT high natural log V2 over V1, okay? That's going to be our governing equation as far as calculating the heat transfer from the high temperature reservoir. Now let's take a look at this and see what we got, what we need to get and what we already know. Let's see, I know the mass of the air. Of course, I know the gas constant is air. I know the high temperature reservoir temperature, TH. V1, in this case, this is V min. Okay, that's V min, but I don't know V2. V2 is some intermediate volume somewhere between V min and V max. Okay? V2 is somewhere in between. So this is V max. V3 is equal to V max, which I have, by the way. I've got this. And V2 is right here. Here's V min. It's some intermediate volume. I don't know what that is. Let's calculate V min. Let's figure out what, I'm sorry, let's calculate V2. Let's figure out what V2 is given our other information. Let's look at process. Okay, I want to know what V2 is so I can plug it in to get the high temperature heat transfer. Let's look at the process 2 to 3 because it will contain information about state 2. Process 2 to 3. And by the way, that is adiabatic expansion. That's adiabatic expansion. That's process 2 to 3. Well, let's write the energy balance down. Q 2 to 3 minus W 2 to 3 is equal to delta U, which is equal to mCV delta T from 2 to 3. Okay? Now, it's an adiabatic process, so this goes to 0. I know what the temperature difference is, delta T. And I know that the work is boundary work. So this is equal to the integral of PdV. And of course, pressure is a function of, according to the ideal gas law, a bunch of stuff. I'll have an M RT over V dV from V2 to V3, okay? Now, I'm kind of stuck at this point. I'm trying to get a volume, V3, but volume's buried inside of this integral and temperature is not constant. 2 to 3 is not an isothermal process. 2 to 3, temperature's falling. It's changing during the process. I have no idea what temperature is doing at this point. So there's really no way for me to evaluate this integral or disentangle it to extract out V2 the way it stands. Okay? So I think I'm going to take a step backwards here. We're going to write another version of the energy balance. I'm going to write the differential version of the energy balance, differential process. Del Q minus del W is equal to dE, which is equal to du. Okay? That's the differential version of the energy balance. It's adiabatic. Adiabatic, so that goes away. And of course, the work is boundary work. So this is P dV. That's the boundary work. Okay? Now, if we assume constant specific heats, then du is equal to mCV dt. That's from the property relationship. du is equal to mCV dt. That's internal energy, not specific internal energy. Notice everything's capitals in here, all right? Okay, so let's write what I got. I got minus PdV is equal to mCV dt. All right. Now, what's pressure here? From the ideal gas law, pressure is equal to mRT over volume. That's from the ideal gas law, from IGB. Okay, so let me make the substitution here. M negative mRT over V equals, oh, I'm sorry, I forgot the dV, equals mCV dt. Notice the masses cancel out in that equation. That helps. And I get, let's write what I got. Let's write what I got left over. And I get negative RT over V equals CV dt. Oh, I forgot my dV in here. dV equals CV dt. Okay, that's from the energy balance differential form. I'm going to separate variables here and I'm going to integrate. I'm going to take all the temperatures and put them over on the right and leave the volumes on the left. Let's see what we get. Negative. I'm also going to put this R and put it over on the other side of the equation. So I got dV over volume. Keep the dV and the V and put the negative RT over on the other side of the equation. I have negative CV over R, okay? And then I have dt over T. Let's integrate this over the process 2 to 3. So let's integrate this from volume V2 to volume V3, and let's integrate this. And let's integrate this from T1 to T2. The variable of integration is volume on the left, temperature on the right. Well, these are pretty easy integrals to evaluate. Notice that we're assuming constant specific heat, so the CV over R gets out of the integral, and I get natural logs. So I get natural log of V2 over V3 is equal to minus CV over R, natural log T3 over T2. Now let me take the CV over the R term and swallow it up into the natural log. Okay? And then I'm going to raise everything to the eth power. So I get T3 over T2 is equal to, V3 over V2. V3 over V2 is equal to T3 over T2 to the minus CV over R power. So for the adiabatic process, the ratio in volume is equal to the ratio in temperature to the negative CV over R. That's what that's saying. Now let's look at this equation here before we get too excited. I know T3 and I know T2. What are those? T3 and T2 are the low temperature and high temperature reservoir temperatures. So I know these temperatures. So T3 is T low and T2 is T high. Okay, so I know that. What about V3 or V2? Actually, I'm trying to get V2 here. So do I know V3? Well, let's have a look at our TV diagram here. So V3 is equal to V max. I already said I knew it. Yes, I know V3 as well. The only unknown in that equation is V2. And so in theory, I can solve for V2. So V3 is V max. Okay, V3 is V max. So let me solve for V2. V2 is equal to V3, which I know, times T3 over T2. Oops. I'm going to put this in parentheses here. Minus CV over R. And that's to the -1 power. That's to the -1 power. Now, what's this CV over R? What's this CV over R all about? CV, let's see here, the relationship between specific heats for an ideal gas, CP minus CV is equal to R. So this guy here, CV over R, is actually equal to CV over CP minus CV. CP minus CV is R for an ideal gas. Now I'm going to divide top and bottom by CV, and so I get 1 over CP divided by CV minus 1. CP over CP, ZV is K. I've defined that as K previously in the givens. CP over CV is 1.4. I've defined that in the beginning of the problem. So this guy is equal to 1 over K minus 1. Okay? So this guy, V3, T3 over T, oops, T high and T low. T high, T low. Minus 1 over K minus 1 to the -1 power. Let me plug in. Oh, and remember V3 is V max. Yes. Okay, just want to make sure we're consistent here in doing our substitutions. All right, let's plug in V max 0.0254. Yes. Cubic meters. And then I have T low over T high. That's 250 over 300. These both have units of Kelvin, so they cancel out. And then I get minus 1, 1.4 minus 1. And that's to the -1 power. And I get the volume at state 2. Volume at state 2 is equal to 0.0161. 0.0161 cubic meters. 0.0161 cubic meters. So now I know V2. So let's go back up here. Let's calculate the heat transfer. Let's see here, the mass, 0.1 kilograms, the gas constant, 0.286 kilojoule per kilogram degree in Kelvin. The temperature T high is 300 degrees Kelvin. And then I got natural log of V2, which I've got 0.0161 cubic meters over V min. V min was 0.01 cubic meters. Cubic meters cancel out. They better for the natural log. The kilograms, Kelvin, and I get kilojoules. That looks good. And that gives me the final heat transfer from the high temperature reservoir of 4.09 kilojoules. 4.09 kilojoules. kilojoules. So Q high, 4.09 kilojoules. Okay? 4.09 kilojoules. 4.09 kilojoules. Okay, let's calculate the efficiency now. Let's calculate the efficiency. So efficiency is equal to the cycle work divided by the heat input. The cycle work is equal to the heat received from the high temperature minus the heat received rejected to the low temperature reservoir. And of course, that's all divided by Q high. And again, we get 1 minus Q low over Q high. Now, Q low is 3.4 kilojoules. And Q high is 4.09 kilojoules. Kilojoules cancel out. Efficiency better be dimensionless. And I get an efficiency of 0.168. 0.168, or if you like, 16.8%. So the efficiency of my Carno heat engine is 16.8%. 16.8%. So that was the hard way of calculating the efficiency. We actually calculated the heat transfer, QL and QH. There's actually a much easier way to calculate efficiency, for example, a very quick way to calculate efficiency. What is that method? Well, a Carno heat engine is a reversible device. So note, the efficiency of a Carnot cycle is equal to the efficiency of a reversible heat engine, which is equal to 1 minus TL over TH. Remember where we got this from? 1 minus QL over QH for a reversible process is equal to the ratio of the reservoir temperatures. In our case, we have 250 degrees Kelvin and 300 degrees Kelvin. The Kelvins cancel out. Again, efficiency is dimensionless. And I get an efficiency of 0.168. We're a little bit of rounding going off. Or if you like, 16.8%. Same efficiency, to within a certain level of precision. Okay, there's a lot of rounding going off when we do the more complicated calculation. So the efficiency for a reversible device, heat engine, 1 minus TL over TH, gives us the same exact efficiency as if we actually went through the entire calculation by hand. Okay. Very nice. I think that's it for today. That's a lot of material. Take care, ladies and gentlemen.